sure everything is okay. Yeah, thank you very much for the introduction from the chair, and I would like to welcome all of you to join my defense, and I will start now. So my title is 351 Silicon Transceivers based on micron transfer printing. My name is Jing Zhang. So basically, everybody already know that we are living in such a highly developed society. We're surrounded by the social media, so many social medias, and also internet things. And every day you use different applications. You do everything on many things online, and you can see there is a chart that indicates how many time or how much money you spent online in just 1 minute. Such a huge number shows everywhere actually, which means the system or optical communication system is so busy, it's so crowded. Coupled with this property of the internet, what happened is the consumption of the electricity power. From this graph, you can see that there is an exponential increase of the power consumption of this whole networks, and it reached 20% of the total electricity consumption in 2030. That's a huge amount of power. But what actually support this highly developed internet? Apparently, one key enabler is optical fibers. But how optic fiber carries the information and deliver this information to every corner of the world is basically lay on the total internal reflection, which you can see from this picture. If the light propagate a medium and it hit the interface between two different materials, you can see a refraction. Actually, is a light bend when the index of the material changed. And when you increase incident angle, the angle of the refraction also increased. But at some point, you will see that the light just totally reflected back into the original medium. So in this way, we can build a stack layer. For example, there is a high index material surrounded by the low index material. If there is incident on this stack layer with a relatively smaller angle, let's say less than the critical angle, then the light will bump at the interface all the time. Then the light optical power will confine in this layer and propagate along it. Then in this way, we can fabricate fiber, which is a very thin silica wire, and is surrounded with also a silica cladding. So it's basically as thick as our hair. Here is a picture of the row of this optical fiber, and probably is tens of kilometers long. But this fiber is very fragile. You need some strings. You need some mechanical support. For example, some strings members and jackets. So there are different types of these fiber cables. So with these fibers, we can deliver the information in terms of light. And one important thing is the material has to have a low absorption or low loss. You can see it's an absorption spectrum of the silica. Here are some windows with very low transmission, very low absorption. And nowadays, our system are really make use of this wavelength band to generate and also deliver the optical signal. And nowadays, with these fibers, we can connect every corner in the world. So these lines actually indicate the optical fiber cables which already deployed on the sea floor. And overall speaking, it's almost 1.3 million kilometers in total. Of course, you have to make sure these fibers are protected, because there are some animals that are quite crazy, they can bite it. Okay, so with this fiber system, we have to realize this connection between each other. But according to the reaching the range of these systems, they can divide it into different layers. For example, long haul, it's very long distance communication, and also the access networks, which will deliver information directly to the end users or subscribers. And actually, most of these errors has already covered by fiber, as linked by fiber, but still some left, some microwire still left in front of our subscribers. In order to realize this communication among each other, apparently you need some devices to send information, generate and send information, and the other side you want to receive this information. And vice versa, you need a receiver at this side and also transmitter in the other end. Then we have the transceiver at each side to generate and send information, and also at the same time receive the feedback. With this system, of course, we need an optical source, which can be used as a carrier. Generally speaking, we use lasers as a source. And here I will explain briefly the principle of the laser. So basically, we need an active medium which could generate light and also amplify light. Here is a two-level system with different energy level. So the electrons of the atom will stay at the lower level because it's more stable. If the electrons absorb the energy, some kind of energy, they will jump to the higher level, but it's not stable. So it will decay back to the lower energy level, and at the same time have some gives a photon, which frequency or this power is equal to the difference of these energy levels. And at the same time, well, yeah, the other case, if there is a photon just incident onto this medium, and the electrons on a higher level will jump back to the lower level at the same time, give out a photon. But this is very special because the photon that emitted from the medium has exactly the same phase and also the same power as the incident photon. But this is not enough for build up the laser. For laser, you still need a cavity. You need a resonant, let the light resonate inside a cavity. And every round the photon pass by the active medium, it have gained some more power or have generate more photons. And after a few rounds or many times traveling through this active region, then you get more photons. Once the gain could balance the loss in a cavity, then you have the laser established. And the laser properties of laser is very obvious. It's monochromatic because the spectrum is very narrow. The phase is really pure, and also is coherent and has a directional output. So other properties of light is the photon can have different wavelengths, and also apparently if you have more photons, you have more power and more intensity. And also this, generally speaking, as a photon or light is electrical magnetic wave, so it has phase. Also, it has a polarization. So with a laser, how can we make a transmitter? If we have a bias current, with bias active devices, it generates light. The power is consistent, and then we need a modulator. If we apply the alternative voltage onto this modulator, the output power will be modulated. Then we can encode the information or encode the electrical signal onto the optical carrier. And there is another way. We can directly modulate the laser. Then we can directly encode the information onto this optical carrier. This structure is more small, robust, and has less power consumption. So at the other side, we want to detect the signal. So we need a detector. Convert optical power to photocurrent. And then we can connect these two with a fiber. Then we have a fiber link. But can we just modulate the amplitude or intensity? Of course, we can do more than that. We can make use of the wavelengths. We can use an array of the transmitter and combine this transmitter together and deliver all the information through one single fiber. But here is very important that each transmitter should work at different wavelengths. And again, we can modulate the amplitude in multiple levels. It's not just a 0, 1, but can be 4, 3, 4, can be 4 levels or even 8 levels. And then we can modulate phase. For example, 100-degree or 90-degree differences, and even more. We can combine the phase modulation and amplitude modulation. And again, we can aid the polarization. So in order to detect or extract the phase, we need a special receiver, not just a detector. We need a coherent receiver. Here, basically, it consists of a local oscillator. It's a narrow line with laser as a phase reference, and 90-degree hybrid, which could mix the incoming signal with a reference, and a balanced detector to extract the information. Because the hybrid could introduce 90-degree phase delay, different phase delay among the output ports, then you can see the expression of this mixed signal. You can use a balanced detector, do an easy kind of a calculation and detection. You can extract the phase. If we plot this detected current onto the XY plane, then you get this constellation diagram. Sorry. And the other thing is, as I said, we need local oscillator as a reference. So which means this reference has very low phase noise, because the phase is coupled with the frequency, so we can measure the line width. If the line width is broad, which means the phase noise is quite large, which will induce some noise to our detected signal. So this constellation will become blurred. And the other thing is, because we use of the local oscillator, we can actually amplify the signal, but without introduce too much intensity noise. And here is an example of the phase noise, the impact of phase noise to this detected signal. You can see the signal become more cloudy, and in some points is completely merged together. We cannot recognize any points of the signal. So basically speaking, local noise, a local oscillator needs a narrow line width, let's see, at least 500 kilohertz. So we have the coherent communication. We can also do the intensity modulation and direct detection. But which one should we choose? Of course, it really depends on the cost, power consumption, and also the performance. We have to strike balance between these two. So following the success of the electronics, apparently smaller means cheaper and faster. So we want to squeeze everything into the small module, and then we can reduce either cost, also make it faster. Here is an example. Is an integrate the coherent receiver. It's quite small, but here it has no laser, and then we have to embed this laser together with this module inside of this module. So the way to do this apparently is photonic integrated circuits. And here are some examples showing the power consumption and also the density per 100 gigabits for the coherent transceiver modules. Apparently, the power cost and footprint is dropping every year. So which platform can we use to make this photonic circuits? There are some candidates. For example, silica on silicon, which is quite similar as the optic fiber with a silica core and also the silicon dioxide colliding, but index contrast is quite low, which means the core has to be very large to confine light. And also there are some other candidates. You can see the contrast, index contrast between the core and the colliding, and also the band radius. It's just reversely proportional to each other. So here, these two candidates apparently is more interesting. The 3.5 semiconductors, which could realize passive and active functions, but it's relatively expensive. And the wafer is a bit smaller. And the other side is silicon on insulator. It's cheap, high yield, and it's compatible to CMOS technologies, but there is no light source on it. But apparently, we stand this side. Here is a roadmap of here is a paragraph show that the cost of the silicon photonics chip, apparently it can go very low. So where we stand? Apparently we're standing on the shoulder of giants. Silicon photonics technology developed by many foundries. Here is an example of the UGent-imec IC50 platform. There are many high-performance devices available on this platform, like germanium detectors, modulators, and other passive devices. And today it's already available on 200 millimeter wafers, and is moving to 300 millimeter wafers. But how to integrate the laser onto it? We can integrate the 3.5 onto the silicon, but it sounds very difficult to directly grow the 3.5 material onto the silicon substrates. Here are some work has been done in our group. You can see this reach grows on the predefined resizes, and also there are some work due with this optical coupling from the 3.5 to silicon waveguide. And the other way is to grow a thick buffer layer on the silicon substrate. And electrically pumped laser already demonstrated, but because of this thick buffer layer, the optical coupling between the 3.5 to silicon layer is quite difficult. So apparently still a lot of work has to be done. So what technology we using today? There are some examples. For example, flip chip integration. In this way, we can fabricate active devices on the source wafer, like 3.5 wafers. And then we can pick and place or just flip chip these devices onto the wafer, but we have to do it sequentially, so one by one. It's really time consuming. And the other way is 3.5 on silicon wafer bonding. We can transfer the 3.5 film onto the silicon substrate and do the post-processes on the silicon substrate. Here is an example of the multi-die wafer bonding. Intel already released the commercialized transceiver modules with integrated laser source through wafer bonding. But still, there are some challenges faced by wafer bonding. For example, if you want to integrate different materials, it's really challenging because the precise flow is different and thickness of the material is different. And the other way is we have silicon photonic circuits. We have to open the backend circuits and integrate 3.5. But we have to open relatively big resize. And the other way is we integrate 3.5 in the backend precise flow, but you have to modify the backend precise flow. That will take quite some effort and also money. Here we go for the microtransfer printing. Microtransfer printing is a normal technology which could release and transfer print a very small device or material films. But in order to realize the transfer printing integration, we have to make sure that the devices can be released from the native substrate. So here we have to incorporate the release layer, which can be selectively removed to suspend the device. So following this process, we first pattern the device layer, and then we encapsulate the device layer. And at the same time, we define the tether structure, which can anchor the device during and after the release edge. Then we can pick up the device, use a stamp, and transfer print onto the target substrate. So which release material can use? The candidates, there are some candidates. There was some investigation on this, the etching of this release layer. And for example, there is 1 micron thick ingots, and also the indifosphor aluminum arsenide. Apparently, indium by aluminum arsenide is much better. Etching rate is much faster, and also the selectivity is better. So how can we do the picking up and printing? The mechanism is based on this, let's say, velocity-dependent addition between the films. For example, if you use a stamp attached onto the device, if we pick it up at a very high velocity, then the adhesion between the stamp and the device is very strong. Then you can break the titers and pick up the device, and vice versa. We can print onto the target substrate. Here is explaining of the. You can show the stamp which we use for the transprinting. Actually, made of a PDMS, which is transparent. It's also soft. You can plan overdrive. You can actually price it, and also you can apply the lateral shear force, and also you can pick up different devices with different thicknesses, and also because it's transparent, you can see through it and do the alignment. Here's a system, and you can see the small pink wafer is a source, and also the bigger one is target. The other one is used to clean out the stamp. So one thing I have to mention that position tolerance of this system is around 1.5 micron. We can go better if we transprint a small array of devices. So with transprinting, we can integrate the different devices close to each other, and also we don't need to open the big area of the backend layers. So it's just like a combine of the advantage of flip chip and pick and place, and also the die to wafer bonding. So here with transprinting, we can also save the materials because we just use a very limited materials, and also we can reuse. Potentially, we can reuse the substrates. But if you do wafer bonding on pick and place, this very thick substrate will consumed, actually, or just leave on together with the devices. So what did I do in my PhD years? Basically, I focus on two parts. One thing is to transfer printing the fiber to the home transceivers. The other one is the coherent receiver. Okay, let's start with my work. Then fiber to the home. There are different kind of systems to realize a fiber to the home. Basically, there are three point-to-point active optical networks and passive optical networks. The first one, apparently, you have every subscribers have a dedicated fiber line, and also the transceiver in the central office. With this you have a higher bandwidth and good isolation. It's more safe, but apparently it costs a bit more. And for the active optical networks, you have the active switches in between. You can switch to make sure that the signal can deliver to the dedicated subscriber by switching. And also you can use passive optical networks. At least there's an advantage and disadvantage of this system. But in this work, we'll focus on the point-to-point because the layout is more simple. And if we can fabricate low-cost transceivers, that might add some values to these systems. So here is a schematic of these transceiver systems. We use a C-band wavelengths to carry the downstream signal, and also we use O-band wavelengths to send information from the subscriber. We will deal with these transceivers, which can be used in a central office site. So here is a schematic of our transceiver. We use micro ring resonator to encode the electrical signal to the C-band wavelengths, and we use a 3.5 detector to receive the O-band incoming signal. Here, a key point is selective of this 3.5 absorbing layer. You can see here, if you use InGASP, there is a very sharp stop band around 1.4 micron, which means with higher wavelengths, longer wavelengths, it will be transparent, but below 1.4 micron, it will be absorbed by this material. So in this way, we can send the light through this waveguide grating coupler and couple through this 3.5 detector to the fiber. And here is our 1.4 channel transceivers. So our target is integrate this device, these detectors onto the grating coupler. And this is a precise flow. It's very standard precise flow for the 3.5 post fabrication. And here we define these detectors on the substrates, and then we protect the side walls of this, protect the meso of the detector, use a silicon nitride, and then we release it, use iron chloride. Then we're ready for transprinting. After transprinting, we just need to deposit metal contact pads. And in the printing, because we don't need very high alignment accuracy, so we just use a machine to do the automatic alignment and print it. It's very easy. And here is the responsivity of the devices. Bandwidth, a small single bandwidth of the detector is around 10 gigabit, 11 gigahertz. And then with this Fabricate devices, we demonstrated 10 gigabit per second bidirectional operation. The second one is a single channel fiber to the home transceiver. Here we use a directed modulated laser, and the other side is still O-band photodetector. So for the laser fabrication, we first transprint. We first pattern a film coupon, a material coupon on a native substrate, and then we release these coupons and transprint onto the substrate. Here we use a silicon insulator. Well, actually, it's a photonic circuit where we already pattern the grating and also the waveguide structures. And after printing, you can see this coupons well sit on the substrate. And then we can do the post precises to define the taper structure and align this 3.5 taper structure to the underlying silicon waveguide. After a few rounds of optimization, we demonstrate our first single mode DFB laser. And you can see here shows some merit results. And the grating we use is a second order grating, and the length is around 300 micron. And because we use MA6 aligner, mask aligner, so it can be aligned very well. The misalignment is below 300 nanometer. So generally speaking, the performance of this device is comparable with the DFB laser demonstrated through die-to-wafer bonding. So next is the demonstration of this single-channel fiber-to-the-home transceiver. So here we already have the DFB laser. We transprint this photodetector onto the grating coupler, and then we do the extra metal deposition. And this device also operates at a 10 gigabit per second. And because of the high kappa L, so the bandwidth of this small signal bandwidth of the DFB laser is around 7.8 gigahertz. It's I think it's just okay for this 10 gigabit per second operation. So the next is the integration with 3.5 on silicon coherent receivers. So here, as already discussed, we need a narrow line with laser as a reference to extract the phase information. So here is formula which explains the line width of the laser. So generally speaking, to achieve the narrow line with laser, we need a low cavity loss, and the cavity has to be long as possible, and also a high output power. And the other thing is the use of the active medium, because different material has different line width broaden effect factor. So, for example, the quantum dot material will have a much lower broadening effect, but the quantum wire normally will give something like 3 to 4. The other thing is we need a stable pump. So here, before demonstrating a tunable narrow line with laser, one thing is very important. We make sure that the transfer printing is workable. So as we already discussed, the transfer printing allows for the 1.5 micron alignment accuracy, but normally the laser integrated through wafer die-to-wafer bonding requires something like less than 300 nanometer misalignment, as we already discussed in the integration of the DFB laser. So first thing we have to address is the tolerance of this 3.5 to 3.5 on silicon coupling. So here we have a simple design. There are two ways to go to realize this alignment tolerant taper structure. One thing is to reduce the optical confinement factor in the 3.5. You can see in the simulation that the mode is almost most of the light is confined in the silicon waveguide. Just leave a little bit expressed into the 3.5, penetrate into the 3.5 active layers. And so and the other way is use a wide 3.5 waveguide. In this way, you can imagine that if there is a misalignment, the small parts of the light that sit in the 3.5 still will not impact by the boundary of this waveguide. It will stay where it should be. And in this way, we can realize the efficient optical coupling. So here we also define a set of the alignment markers to realize its alignment during the transfer printing. So this is simulated results. You can see that the node propagates through this taper structure and gradually coupled from the 3.5 to the silicon layer. And basically speaking, this taper is around 200 micron long, and taper tip width should be less than 300 nanometer, which will fit our post-synthesis flow. And here is the Fabricate the taper structure. You can see this markers we define on the source, and also the taper structure is really narrow. It's just on target, and also this coupon is arranged in a very dense array, and you can see the metal is already defined on the coupon. So after printing, we just need to deposit extra metal contact. So here's our laser design, which is you can see here we use a pair of micro ring with a slightly different FSR to realize this wide wavelength tuning. And here is the transmission spectrum of this cascaded micro ring. You can see the combined FSR is around 40 nanometer. And this is Fabricate devices. It's an array of the tunable laser. Here is a transfer printed coupons, a taper structure LC, and the micro ring is integrated a micro heater, and to realize the wide tuning, and also we use a tunable reflector. Then we can tune the loss of the cavity. And here I show some merit results, and you can see we realize the 50 nanometer tuning range, and also the output power is above maximum output power reaches almost 6 dBm, and also we can realize continuous tuning over the OR tuning range. And we also did some line width measurement, which indicates the around 300 kilohertz minimum line width. And the other thing we tried is 3.5 silicon integrated coherent receiver on the passive opaque photonic circuits. Because we can demonstrate laser on the passive photonic circuits, we can transfer print a photodetector, 3.5 photodetector onto the photonic circuit. If we can combine these two together, then we can build up the transceiver. This work, well, due to some reason, this work didn't continue, but the precise flow goes very well. The other thing is the integration of the transceivers, coherent transceivers on the IC50G platform, because we already have the germanium detector, which has really good performance. And we have other building blocks like a phase shifter, some tuning elements, and also have very good grading couplers with low loss. And all these building blocks we can use to build out to design a coherent transceiver or receiver. So here, first we try this receivers without the integrated laser. And this receivers is integrated with TIA array, and which is mounted onto the PCB board. And this with this device, we demonstrate 28 gigabaud QPS key, and also even 16 quad. So this demonstration shows that our receiver design is good, and we continue with our work. So the next step is integrate the laser on this platform to realize a fully functional coherent receiver. But here we have to note that the silicon device layer on this platform is 220 nanometer. Luckily, there is a polysilicon layer above this crystalline silicon is around 160 nanometer. Although it's not very ideal because the relative high loss, but we can always do some design to optimize the loss of the device. So again, if you want to demonstrate laser, we have to address this issue, how to couple light from 3.5 to silicon. Here we still follow the previous design. We use a linear taper and use a wide 3.5 waveguide and also relative narrower silicon waveguide. But here we use a broad polysilicon to make sure that the bottom surface of the substrate is flat, which is good enough for the transfer printing of the 3.5 coupon. And here shows some simulation results. You can see the mode could couple into the silicon waveguide, but because the thickness of our silicon layer is a bit thinner, which makes the taper much longer to realize the efficient optical coupling. And here's additional simulation to see how much power could couple from this let's see, polysilicon layer to the crystalline silicon layer. And we did the first try. We transprinted the SOA firstly onto the IC50G platform, and you can see we get just above 10 dB small signal gain, and also the gain spectra is around 35 nanometer. Because we use a relatively shorter coupon, it's around 1 millimeter. So and also because confinement factor in the active region is relatively low, so the gain is not super high, but it's already good enough to build up a laser. So with this result, we can further design a laser cavity. As we already discussed, we use micro rings to filter out the longitude mode in a cavity to realize a single mode operation. So here first we investigate the performance of the micro ring resonator on this platform, and here shows some results of these rings. And basically we can have the relative high loaded Q factor, and also the drop pot loss is not is acceptable. And here is a cascaded micro ring resonators, transmission spectra of these resonators. And here is our design, which combines the receiver together with integrated tunable laser, where you can see these micro rings, and also the area where we want to transfer print to the 3.5 amplifiers. So basically speaking, everything is ready. We have all the building blocks. We can realize we should be able to realize this coherent receiver on this platform. So here I will draw a conclusion about what I've done in the past few years. Again, so basically we demonstrate transfer printing fiber to the home transceiver, and to to realize these transceivers, first we demonstrate the transprinted O-band photodiodes. Because we select the spectral 3-5 semiconductors, so we can have the absorption of in the O-band wavelengths, and we can realize a transparent. This material is transparent in a C-band, so we can duplex these two materials to two wavelengths. And the other one is we demonstrate the transfer-printed DFB laser. So with this laser, we can co-integrate it with an O-band photo detector. Then we can realize a very simple transceiver. The other part of the work is focus on the coherent receivers. So again, we have to deal with the optical source. We first demonstrate the transfer-printed tunable laser, and the performance is acceptable. We can realize less than 500 kilohertz line width, and also the tuning range is over 14 nanometer. And we try to integrate this photo detector and receivers onto the passive photonic circuits. Process flow works very well, but further work has to be done to optimize everything to realize the functional receivers. And the last thing we tried is to realize the coherent receiver on the IC50G platform, because everything, well, many building blocks with high performance is ready there. We just need to integrate the laser onto this platform. And in the first try, we already integrated the amplifiers onto this platform. Performance is acceptable, and also we have a building block like a micro resonators and other stuff. We can build up the tunable laser, and because we already demonstrated the receivers with the external laser, so everything's ready. We can do the next. We are ready for the next step. So. What's the next? Here, currently I'm working on a C-band 3.5 on silicon circuits, of course, to realize these transceivers. And because, as I said, the quantum dot material could provide a less line width broadening factor, so it's more promising for the narrow line width laser. And because it's insensitive to the temperature, or we can see it can work on a high temperature, something like 80 degrees, which is also very good for realize the low cost transceiver. So, and also with the transfer printing technology, we can do the integration of some other materials like lithium niobate or some 2D materials, and maybe some other 3.5 device, some other 3.5 materials or devices onto the photonic circuits. Yeah, that's what I have done in the past few years. That's all my work. Thank you very much for your attention.